Okay, this is Philip Griffiths. I'd like to welcome everyone again to this second talk in the workshop on Hodge theory and rationality. Our speaker is Yuri Tschinkel, who is a student of Yuri and has done wide-ranging and extremely interesting and varied work in rational geometry, rationality, blending these Russian, European, and American schools, and obtaining many very interesting results. Yuri, welcome, and thank you for agreeing to give this talk.
Well, thank you so much for this very kind introduction. I will be speaking about joint work with Maxim KONTSEVICH and Pestun, as well as Brendan Hassett and Kresch. And the kind of questions that we study, well, rationality, of course, stable rationality, and the main problems in these areas, as far as I understand, is classification by rationality properties, which varieties are rational, which are not. And then we would like to study compatibility with basic geometric operations, behavior under deformations, as well as specialization. And then we would like to introduce computable abstractions to rationality and stable rationality, and study invariants that arise in this area, and their applicability perhaps to some other questions in algebraic geometry. Now, the questions of rationality are interesting over algebraically closed fields, but also over non-closed fields, as well as in presence of group actions. And that was recognized early by Manin and Skotsky, who studied G surfaces. And G, in their study, was the Gallo group of splitting field, the field for which all the exceptional curves are defined, well, or the automorphism group. Now, in this talk, I will focus on group actions, on the study of equivariant birational geometry. So G is a finite group. We will work over an algebraically closed field of characteristic 0. We will have a smooth projective G variety X, regular G action, and to look at the fixed point locus. So let me recall some basic facts about this situation. So if G is cyclic, acting on a rational variety, then we are guaranteed to have fixed points. If we have a G equivariant birational map between smooth projective G varieties, and the group G is abelian, then the presence of fixed points on one is equivalent to the presence of fixed points on the other. So this is a very useful property, which allows to check, G equivariant birationality in some cases. And finally, there is a cohomological invariant studied extensively by Manin and later by Coyote-Len and many others. So if X and Y are smooth projective G equivariantly stably birational algebraic varieties, then the group cohomology, H1, G is coefficients of the Picard, is preserved, is the same. And in fact, for all subgroups G prime of G, and this property is called H1 triviality. So here is a theorem by Bogomolov and Prokhorov that if G is a cyclic group of order P, a prime number, acting on a smooth rational surface and fixing a curve of genus at least 1, then we are guaranteed to have non-trivial H1. In fact, H1 G with coefficients in Picard is Z mod PZ to the 2G, which is the genus of the curve. So there is a generalization of this result to cyclic actions, not necessarily of prime order, but under the assumption that all stabilizers are either trivial or full, the full group G. And then indeed H1 G Picard is computed by summing over all occurs in the fixed point locus, as a fixed locus for the G action. So one can try to understand H1 trivial surfaces, del Pezzo surfaces, for example. Well, there is sort of the condition of G minimality that's relevant. In other words, you can't blow down any G orbits of curves. So, and the result of Prokhorov is that if you have a del Pezzo surface of degree less equal than 4, then H1 triviality and minimality implies that there is only one such surface, an explicit degree 4 del Pezzo surface, and the group is the one written here. And in the same paper, Prokhorov also classifies conic bundles with this property. And this work has been completed. There is a very recent preprint on the archive by Sarikian, where he looks at non-linearizable actions on del Pezzo surfaces of degree bigger or equal than 5. Non-linearizable meaning not equivariantly birational to linear actions. So of course, then the question is, are H1 trivial G actions stably birational to linear actions? And so this is still open. And in particular, this TP4 will be very interesting to look at. Another important result I want to mention by REICHSTEIN and YOUSSIN concerns actions of abelian groups, namely linear actions. So suppose we have a d-dimensional faithful representation of some abelian group, like 2 of those. So we can look at characters of G appearing in one and in the other, so eigenvalues. So then the theorem is that V and W are equivariantly birational if and only if the determinants are equal up to plus minus 1. So this condition is only meaningful when the rank of the abelian group is equal to the dimension. If it's bigger than the dimension, it's not faithful. Even if it's smaller than the dimension, then you're finding 0 equals to 0. And indeed, in this case, the representations are equivariantly birational. So in particular, cyclic linear actions on Pn with n bigger or equal than 2 are all equivariantly birational. Now, I should also mention here that if you take 2 representations of the same finite group G, abelian or non-abelian, then they're equivariantly stably birational. So when you apply this criterion of REICHSTEIN and YOUSSIN, you produce examples, representations of abelian groups that are stably birational, but not necessarily birational equivariantly. So the starting point for my work with Maxime was, can we introduce finer invariants of, let's say, actions of abelian groups? So now let's focus on abelian groups. Let A be the group of characters. Let X be a smooth projective n-dimensional variety with a regular G action. Look at the fixed point locus, so could be isolated fixed points or some strata. And now look at the weights of G in the tangent space at some point X alpha in F alpha. And let's record those characters. So of course, it's an unordered n-tuple of characters. And what you would like to do is you would like the invariant to be exactly this. Take the variety X as G action and assign to it a sum over these symbols. Now, for this to be an equivariant birational invariant, we need some relations on these symbols. So we want to make sure that if we look at a G equivariant blowup, that nothing changes. So in other words, the difference between these assignments should be 0 in the group that captures invariance. Well, on the face of it is sort of a complicated proposition. So what kind of blowups can you have? Of course, we have an equivariant weak factorization that tells us how to factor equivariant birational maps. But nevertheless, you're blowing up any G-stable subvariety in X and try to find out what's going on. It turns out that all of this can be formalized in a completely transparent way as follows. So consider the Z module, let's call it Bn of G. This is generated by unordered n tuples of characters of our group G with the following two properties. So the first property is the generation condition, so that the characters actually, the sum of the AIs, I mean, anyway, they generate the group A. And the other more important property is whenever we see collection A1, A2, and then B1 up to Bn minus 2, then this symbol is going to be equal to a sum of the symbols below, A1 minus A2, A2, and then all the others, plus A1, A2 minus A1, and then all the others, if A1 is not equal to A2, and simply A comma 0 if A1 is equal to A2. Well, so those are the relations. Maybe there is some connection to Milnor case theory. You can, well, anyway, that's what we thought when we first saw that. But these are kind of different relations. You know, this final form came about after quite a lot of combinatorics. So now let's go back to where we started. So we consider XG, record the eigenvalues of G in the tangent bundle at these fixed point strata, and then write this sum, and now consider this as an element in the group B and G. So where these symbols A1 up to AN are subject to those two relations that I wrote down. And then it turns out that the class in this group Bn of G is a well-defined G equivariant birational invariant. So there are versions of this that one can study. We can introduce an additional relation where we allow to invert one sign. All right. And so here is an observation that the class of the projective space, Pn, n bigger or equal than 2, with the linear action of a cyclic group, Z mod n, is torsion in Bn of G and trivial in Bn minus of G. So we know that all such actions are equivalent, so we may as well look at the simplest one, where we act by nth roots of unity on one of the coordinates and do nothing to the others. So we have an isolated fixed point and a hyperplane. And then the symbols that we write down is, 1, 0, 0, 0, and then -1, -1, -1. Now, our relation says that whenever we have AA, then you can replace it by A0. So when we see the same entry and everywhere, then doing that relation stepwise, we arrive at -1, 0, 0, 0, 0. So in other words, we're looking at 1, 0 plus -1, 0. Now, the fact that it's 0 and Bn minus of G is obvious because that minus sign goes out and then we see, this minus this is 0. So I want to show you a proof that this is torsion in B2, just so that you see some proof in this business. So let's introduce a slightly different symbol with angle brackets AB, which is A comma B if they're not equal, and 1/2 A comma 0 if one of them is 0. Okay? So the advantage of using these brackets is that previously the condition was A comma B is A minus BB and AB minus A, but only under the assumption that A is not equal to B. Now, if A is equal to B, well, then the previous condition in the angle brackets was, AA equals to A comma 0. But here we get uniformly. Even when B is 0, we find, because of that 1/2, we find exactly what we want. In other words, with, I call it blow-up relation holds uniformly for all AB. So now we're going to symmetrize by plus minus 1 everywhere. We're going to consider this element delta AB, AB minus AB minus AA, and so on. And now we observe that it's actually invariant under SL2 Z mod NZ. So our condition is that A and B generate the group Z mod N. So in other words, the GCD of A, B, and N is equal to 1. So we have a transitive action on SL2 Z mod N on this. So we can form a sum over all AB, primitive vectors in the lattice Z mod N squared, not lattice, group Z mod N squared, delta AB. It's 4 times this. And now we can apply the blow-up doubling relation to each term. And we have the same sum with twice as many terms. So in other words, S is equal to 2S, which means that S equals 0. And since all the deltas are the same, we find that delta times the number of elements in this sum is 0. So in other words, delta is a torsion element in B2. And so then the only thing we need to do is to put B equals to 0, and then we see A0 plus minus A0 is torsion. And so A equals 1, that gives us the class of the projective plane. But as you can see, the relations only involve 2 entries. So whenever we prove something for 2 entries, we have it automatically for all the BNs. Okay, so that was the first step, but then we can introduce a little bit more refined invariants, taking into consideration the birational type of the locus fixed by G. So we could have strata of dimension bigger than 0, and then we could record their birational type and add this information to the invariant. So the condition is as follows. We look at birational equivalence classes of varieties, but the equivalence is with respect to the following property. Suppose our variety is birational to W times some affine space, but not to a product of a variety times an affine space of dimension 1 bigger. So it's like splitting off some affine piece from the variety birationally. So there is no G action on these Y's. And then the invariant for the G action is going to be like this. You're going to take a direct sum over all M from 0 up to N minus 1. And then we have a direct sum over all such equivalence classes. And then the entry is an element in the group B, M plus 1 of G. This is how it works in geometry. So let's look again at the stratification by the fixed point loci. The invariant is going to be a sum of contributions from each of those. And at each of those, we record the information about the function field of the fixed point locus. Namely, if F alpha bumped up to dimension N minus 1, which is a dimension of, N is a dimension of the variety, so up to kind of dividers. If this sits in this class, BUR N minus 1, M alpha of K, then we put this symbol into a copy of BM alpha plus 1 of G. I mean, of course, it has to be digested, but what comes out then is indeed a birational invariant. So the next step, so Andrew Kresch and I took by looking at even more information. So suppose G is an abelian group, then we introduce the group, which you call Burn N of G, the equivariant Burnside group of G, to be the quotient of the Z module generated by symbols. So the symbols are triples. So H and G mod H acting on some, well, it's a Galois algebra over a field of some transcendence degree after isomorphism. And then beta, which is a faithful n minus d dimensional representation of H, modulo blow-up relations. So the blow-up relations are a little bit complicated. I don't reproduce them here. They're in the paper. But so let's go to the computation, and it will explain what these symbols are. So computation is computed, I mean, the invariant is computed on a standard model in the terminology of REICHSTEIN and YOUSSIN. So X is smooth projective. There is some Zariski open with free action of G. The complement is normal crossings, and then comes kind of the relevant condition is that whenever you have an irreducible component in the complement on the boundary, then either the translate of this component doesn't intersect the component, translate by G, or G acts on the component. And it turns out that you can achieve such a model after equivariant blowups, and once you have it, it will persist. And so this is how the invariant is computed then. So we sum over all strata with generic stabilizer H, and the symbol here records the eigenvalues for H in the normal bundle to the stratum F, so that's this piece. And then it records the action. Well, some of the action could be on the function field of the stratum, but then the strata can also be kind of moved around. And so this G mod H records exactly that. So it's partly an action on F, on the function field of F, and partly translation. And this is, you know, G mod H Galois algebra. So, and the relations that we impose that are completely explicit give us a G birational invariant. Those are the new invariants. And now, of course, you want to connect those. If you look at the Burnside group, then you can take a quotient by the subgroup generated by all symbols where H is a proper subgroup of G. In other words, where the stabilizer of the stratum is not the full group G. So then that quotient, Burn N G of G, subjects onto B and GK, and that subjects onto B and G. So this new thing that we introduced is a refinement of the previous ones. For surfaces n cyclic, and n equals 2 and G cyclic, we recover Blanc's theory of what he calls normalized fixed curves with action that allowed him to completely classify abelian actions on surfaces. For surfaces, again, n equals 2 and G cyclic of prime order, the invariant that we introduced encodes the H1 of G Picard, the invariant studied by Bogomolov and Prokhorov, simply because if you have a curve of genus at least one as a fixed point locus, it will show up and is one of our symbols there. So abelian actions on surfaces are completely understood. All such actions are linear, provided there is no curve of genus at least one in the fixed point locus, and provided it's not this one exceptional type where you have a fixed point free action of Z2 times Z4. So, well, if there is a curve of genus at least one on XG, of course it will appear on equivariant on every equivariant birational model or invariant captures with. So in a sense, B2 of G is kind of boring. It doesn't give anything new in dimension 2. However, in the group B and GK, we saw that the invariant combined information from BMs of G for M less than N. So in particular, it can contribute non-trivially to this invariant B and GK, and I will show you examples how it does so. Now, in dimension 3, abelian actions are not completely understood, but should be accessible via equivariant minimal model program. So in the examples that are to follow, I will focus on dimension 4. We do not know how to systematically factor birational maps in dimension 4. In particular, we do not understand rationality or failure of rationality of cubic fourfolds. So I want to show you how these invariants that are introduced provide some information, new information in these cases. So there's, of course, a very extensive literature on automorphisms of cubic fourfolds and on their variety of lines. So I'm just citing Klada, Zheng, Fu, Mongardi, Mayansky, Auchi. So there is a long paper by Mayansky with a classification of abelian actions on cubic fourfolds, and I consulted that extensively, that paper. So let's look at cyclic actions. So these are the possible cyclic groups acting on cubic fourfolds. So, well, to get something non-trivial, that group B, let's say, using the group B4, we have to have that this group is non-zero. It turns out that it's actually 0 for all n less than 27, n equals 30 and 32. So 27 doesn't show up here in this list. And the only possibilities therefore are n 33, 36, and 48, if you wanted to use the group B4 only. So these cubic fourfolds are rigid and explicit equations. Are these rational? Not sure, but it can be answered, at least conjecturally. So we can also look at torsion in our groups, and then we get a little bit more. So we get non-trivial torsion mod 2 for n equals 16, 24, and 30, things that were not accessible previously. And so there's also some 3 torsion that showed up. So let's do concrete examples. So consider this fourfold, this equation, which has an action of z mod 36, and these are the weights. So 0 means there is no action on x0, weight 4 on x1. So let's compute. So this is going to be 8, and x2 is 28. 8 plus 28 is 36. So each monomial here is weight 0. So they're isolated fixed points, and the fixed points are 0, 1, 0, 0, 0, and so on, 0, 0, 1, 0, 0, except the point 1, 0, 0, 0, which is not on the fourfold. So for each of those, I can compute the weights and the tangent spaces, and I get this collection of symbols. And now I need to check that the sum is non-zero in the group B4 of z mod 36. And indeed, in this case, the projective space gives 0, and the cubic fourfold gives non-zero. And so the conclusion is that this cubic fourfold is not G-equivariantly birational to P4, this linear action of z mod 36. All right. So now let me show you the application of B and GK, the more refined invariant. So I look at the action of z mod 8 on this cubic fourfold. Here F3 is a cubic polynomial in x0, x1, x2, and F1 is linear. And so the weights are 0, 0, 0, and then 1, 6, 4. So 1, so it's going to be 2 plus 6, so 8. So B4 of z mod 8 is 0, as I mentioned before. However, here we observe that there is a curve fixed by the action, namely, if you put x0, x4 equals x0, then f3 equals 0. It's a cubic curve on P2. It's an elliptic curve, in general, f3. And so this elliptic curve, well, it's not stably rational. So it happens to be, okay, one of the terms in the group BNGK, but we need to check that the elliptic curve is coupled to a non-trivial element in the corresponding B group, and indeed it is, so that we get the non-trivial contribution to BER3-2 from the function field of this elliptic curve in the fixed point locus on this fourfold. So, okay, so this cubic fourfold was not equivariantly birational to P4, and here the computation in the previous case, on this slide, I mentioned that we have to compute, 400 something thousand linear equations and 82,000 variables to determine that this sum of symbols is non-zero. But now we are in a much smaller group, and so we only have to solve 200 linear equations and 120 variables on computer, of course. And so the conclusion is it's not equivariantly birational to P4. Now let's look at the next example. This cubic fourfold is actually rational. There are two disjoint planes on it, so given by these equations. And we have a Z mod 6 action with these weights. So what happens here is that we're going to use that invariant Burn N of G, the more sophisticated invariant, where we take into account not only loci with maximal stabilizers, but loci with stabilizers proper subgroups. So there is actually a cubic surface with stabilizer Z mod 3, and what's essential, the correct normal bundle data, normal bundle weights. This is how the equation was picked. And so that cubic surface, well, we'll get a symbol. So this is a stabilizer. We have a function field of a cubic surface. And then there is a Z mod 2 action on that cubic surface, which fixes an elliptic curve on the cubic surface. And as I mentioned, the weights are chosen appropriately so that this is non-zero. Now, when you have a cubic surface with a Z mod 2 action which fixes an elliptic curve, then that cubic surface is not stably equivariantly linearizable. That's the theorem of Prokhorov and Bogomolov I mentioned. Once you have a curve of genus at least 1 in the fixed point locus of some element on the surface, and H1 of that cubic surface is non-trivial. So in other words, this symbol in the equivariant Burnside group, Burn 4 of Z mod 6, is non-zero. It doesn't interact with any other symbols there. And so this rational cubic fourfold is not equivariantly birational to P4 for the Z mod 6 action. Now, so I should make a few comments. So rationality of cubic fourfolds without any group actions, of course, one of the central problems in the field. It's supposed to be linked to, if you take the categorical approach, then there's some K3 category, K3 something, but it's sort of in the middle cohomology. So here we are looking, and these are the extra classes that are supposed to govern this. So here we're looking at things in a multiple of a hyperplane class, an elliptic curve, which happens to lie on a cubic surface, also like a multiple of a hyperplane, and which happens to have some normal bundle weights and something else. So in other words, we have no idea how this couples with the invariants that show up in the derived categories. How that's supposed to couple with the K3, we don't know, but so this is what we have. Okay, so now I want to talk a little bit about non-abelian invariants. So we have, let's say, finite non-abelian group. Then we look at the Z module generated by symbols. H is an abelian subgroup. Action of a normalizer, again, we have an NG of H over H Galois algebra over a field of transcendence degree most n over our field up to isomorphism, and then there is some faithful n minus d dimensional representation of H, and then again there are some blow-up relations. And so the invariant of variety is computed on a standard smooth projective model. And on that, in particular, the only stabilizers that we have are abelian subgroups of G. And so we sum over all abelian subgroups of G. We look at the corresponding strata. We look at the weights of the normal bundle to the stratum. And then we have the normalizer action on the function field of the stratum or translation action of the different components, so kind of an orbit. And so we encode this, and to look at the group of symbols factored out by the relations, and that's an invariant. So, okay. Now, you would like to understand specialization. And specialization entails recovering sort of the birational type of the variety from some kind of smaller dimensional loci, some combinatorics of strata in smaller dimensions. And so, well, we introduce invariants of quasi-projective varieties, where the naive invariant is just the same. You simply look at strata which are in U with generic stabilizer H and record those things. So again, it's a G birational invariant. However, with this definition, the boundary does not carry enough information about the open piece and the action of G on the open piece. So when we realized this, we introduced this more sophisticated version where the invariant is actually, well, you look at some compactification of your quasi-projective U, where the boundary is smooth normal crossings, and again, acts as a standard model, and we have a stratification by these intersections. And then we record the normal bundle, the total space of the normal bundle, together with the G action. And then when we take this alternating sink, we'll get the correct invariant of the quasi-projective variety. And then imitating this construction in the relative situation over a spectrum of a DVR, where you could think of the special fiber as being sort of the complement to some U, we obtain the following theorem: specialization, homomorphism. So let O be a DVR with fraction field K and residue field little k, characteristic 0. So in our paper, we assume that K contains all necessary roots of unity. Here in this talk, K, you may think of K algebraically closed. Fixing a uniformizer, we get a well-defined homomorphism from the Burnside group for the field of fractions to the Burnside group of the residue field. So how does this fit in? It has been tremendous progress in the study of rationality, ushered in by the pioneering work of YOUSSIN, integral decomposition of the diagonal based on law Srinivas. And then further developed by Kulot-Telen and Pirutka, where universal CH0 triviality was a condition that was first introduced and studied under specializations. And then Nikes Schindler, who showed that stable rationality specializes by using the K0 varieties module of the class of the affine line. And then Maxime and I generalized this by simply looking at Burnside group, which is free abelian group on birational types, on equivalence classes up to birationality of algebraic varieties, and we showed that a class in the Burnside group specializes directly. So So here is the analogous theorem in the equivariant context. So here it's formulated as follows. So suppose you have two smooth projective varieties over capital K with generically free G actions admitting regular models, which are smooth and projective over the integers, and the G action extends to those models. So if X and X prime are equivariantly birational over capital K, then so are the special fibers. So this, of course, is the simplest statement where you have a smooth family, but interesting applications come from allowing mild singularities, and we also introduce a notion of what we call BG rational singularities that allow to understand the equivariant birational types of special fibers as mild singularities. And in particular, you might extract more information about the general fiber by finding new obstructions to equivariant birationality in the special fiber. So as before in that little lemma that I showed you, where we passed from the square brackets to the angle brackets, we did a lot of numerical experiments and realized that there is kind of a meaningful simplification of defining relations. So we introduced closely related groups that you call a modular type, Mn of G, which is generated by unordered tuples of characters of our abelian group G. Again, the relation of generation condition is in place. And then the blow-up relation is just as before, where only the first two entries show up, and nothing else. So we saw this already for B2. Now, there is actually a map from Bn of G to Mn of G, and you do nothing if all the entries are not equal to 0. You just change the bracket. If you see 1 0, you put a 2. And if you see 2 zeros, you put a 0. And then you extend by linearity. So in that paper with Maxime and Pestun, we showed that it's actually well-defined homomorphism, subjective. In more recent work, we showed that tensor Q, it's an isomorphism. So in other words, tensor Q, you may as well work with the M groups, and let's look at what these groups are. For n equals 1, the generation condition says we're looking at residues mod n that are coprime to n. All right, so that's our group. For B2, let's say cyclic group Z mod P. So then we look at symbols A1, A2, GCD A1, A2, P is 1, with this kind of condition that I mentioned several times. And the angle brackets is the same. And the only difference is here in red that I also mentioned, AA is A0 or AA is 2A0. All right. So suppose you want to find out, well, what's the dimension of this group M2 of G? So we have to solve linear relations over Q, vector space spanned by these symbols. And how many symbols do we have? A1, A2, they go from roughly P squared. And those are the relations. So, and you have P squared linear equations, the same number of variables, and you start computing, and you find P squared minus 1 over 24 plus 1. So, okay. Now, for n bigger or equals than 3, if you want to compute B3 of Z mod P, then you find that the system of equations is highly overdetermined. And so it's really striking that we find this formula for B3 of Z mod P. So P minus 5 times P minus 7 over 24, which is kind of the previous thing, minus P minus 1 over 2. So, okay, compute, but suddenly there are unexpected jumps at P equals 43, 59, 67, 83. So, and again, so for like 83, we're looking at 83 cubed variables and many, many equations. So there are tables that we are assembled. And so here you look at 43. And so this is a B2. And this is a 3,2 is a B3. And then you look at B4 of Z mod 43, and you find there is a 1 there. And you find that B4 is mostly 0, as I already mentioned when we're talking about cubic fourfolds. So, okay, so using all of this, we discovered there is a lot of structure in the picture. So we can consider Mn of G in N and in G. We can introduce this additional relation. And then we found that actually the Q vector space Mn minus 1 of G is a cohomology of arithmetic group, a certain congruent subgroup in GLN of Z with certain specific coefficients. And in particular, the group Mn minus, the group Mn, tensor Q, they carry Hecke operators. They're really arithmetic in nature. So the structure that emerged from looking at these tables, for example, so let's look at this table. Let's look at B3 and look at the first non-zero entry. So the first non-zero entry is for n equals 9. All right, so, and everything is 0 until then. Let's look at B4. The first non-zero entry is at n equals 27. All right, so you see 27, 9, and then you see 3. And so there's clearly some kind of structure, something is propagating. And so to understand this propagation, let's look at the exact sequences of finite abelian groups, corresponding sequences of character groups. And then it turns out that there are multiplication maps from Mn prime, Mn2 prime, where you sum the dimensions. And the multiplication map on symbols is completely straightforward. You sort of lift, you sum over all lifts to A of the thing coming from the quotient of A. And then the other ones you understand as elements in A under the embedding. And so this multiplication also descends to the M minus versions. There are co-multiplication maps as well, which are defined again in terms of symbols. And then using multiplication, co-multiplication, you can map the group Mn. So I put the minus in red because you can look at versions with the minus signs and without the minus signs in there. So you have a map from Mn to Mn prime and Mn2 prime. And then you can sum over all such maps. And you can look at the kernel and you can call this a primitive part. And you can try to understand the primitive parts. And then in this way, kind of decompose your group Mn into primitive pieces. And of course, for M1, there isn't really much to say about the primitive part. But so what we proved then is that if you have a cyclic group, then the Q vector space Mn is actually isomorphic to the sum of all these primitive pieces. Whereas the sum is over all flags, well, first of all, over the length of a flag, and then over all flags of this length. And then you look at the compositions of your n into all possible n1 plus n plus 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 n r. And then for each of those, you look at these kind of terms, and you look at the primitive pieces in those, and that allows you to reconstruct those Q vector spaces from the basic primitive pieces. And the basic primitive pieces that we see, well, we find in dimension 2. So in dimension 2, M2 primitive is actually equal to M2 minus primitive. And that's equal to the dimension of the space of cusp forms of weight 2 for gamma 1n. So at this stage, I should also mention that in subsequent work of Andrew Kresch and myself, we introduce invariance of stacks, quotient stacks, where, again, we look at stabilizers and data coming from stabilizers and things like this. And we have sort of analogs of these groups. If you translate this into symbols, in the simplest case, so you look at eigenvalues, A1 up to AN, but now you use them up to automorphisms of your stabilizer. And if you do that, then the spaces that capture our invariants, the spaces of invariants, the analogs of these B2 tensor Q, they are actually linked to cusp forms for gamma 0 of n. So here, kind of in the first version, we had the modular curve x1 of n, and in the other version, x0 of n. So, well, these things coming out of birational geometry, even for surfaces, is kind of intriguing for me. So in any event, to continue here, the primitive pieces in dimension 3, well, that's sort of a number of certain cuspidal automorphic representations for a congruence subgroup of GL3Z. And in dimension bigger or equal than 4, via computer, we don't find any primitive pieces. And indeed, there are conjectures to the effect that there's nothing there. Conjectures in the cohomology of arithmetic groups theory. So if you want to compute the Q ranks of these groups M Z mod n, well, for n equals 1, it's the Euler function. It's the number of residues co-prime to n over 2 in up to plus minus 1, so because of m minus. For n equals 2, we find sort of a genus of x1 of n. And for n equals 3, we have some mysterious dimensions that show up. The first one for 43, then 50, 51, 59, and so on and so on. And these things kind of propagate. And so for n4, we found no primitives. And here the computations are really huge. So the matrices are, size, 10 million times a million or things like this. So they take several days. So this is what happens. So to summarize, we looked at, we introduced new invariants in equivariant birational geometry. So BNG, which looks at abelian groups acting on varieties and records information only for loci with maximal stabilized as a full group. BNGK does the same, but records also information about the function field of the stabilizer, of the locus stabilized by G, fixed by G. And the Burnside group, equivariant Burnside group, records intermediate subgroups as well, records the action of G mod H on the stabilizer locus and the translation of that locus, the orbit as well. And we saw how to apply these invariants, like in particular cubic fourfolds. And what is emerging now is that these invariants of birational geometry, they're really kind of universal. They have a very intricate internal structure. The connection to cohomology of arithmetic groups, I mean, that to me is really very, very interesting. Multiplication, co-multiplication for the BNG version is sort of established tensor Q. For the other versions, well, we're looking at this right now. And so, so here's the story, and I very much hope that these new invariants can be applied to many more problems. In particular, the study of quotient spaces V mod G, where V is a linear representation of G, to the study of rationality of tori. That is a very active area with important works by, of course, Kolyotilen, Sansuk, and Kuniavsky, Schwarzman, Skarbogantov. I mean, so there are some open questions about tori in dimension 4, where the cohomological abstractions to stable rationality are trivial, but rationality is unknown. So I think that now that these invariants are sort of in place, it would be interesting to deploy them. All right, thanks so much.
Questions?
Excuse me, I have a question. So in the proof, in defining invariant for non-abelian groups, you used the stabilizer is abelian. And can one define not using this kind of special resolution in order to reduce that to abelian stabilizers, just by having more relations on representations of stabilizer or whatever?
So this is a very good question. And in fact, the first attempt was to just do it directly. The answer is the combinatorics becomes formidable. And if you look at the proof, and so the paper with Andrew Kresch, it's a pretty monstrous proof already in the setup that we're using after you reduce to abelian stabilizers. So the answer is yes, it should work. How to organize this combinatorially? Well, we know that it's a birational invariant. We know that whatever you define in the end will be something on the blow up where all the stabilizers are abelian, and then it will coincide with what we define. And well, okay, how do you get there? But indeed, it would be great to have,
the preliminary definition,
yeah,
and
exactly.
yeah, and there is also a question. So in your proof of defining relations, do you consider the so there should be blow-ups in order to write down the relations. There should be blow-ups and G-invariant subvarieties. Yeah, so do you consider different positions of this subvarieties with respect to fixed locus?
Absolutely. So that's the whole point.
Yeah, so just a brief question. So there should be a transversal case and a non-transversal case. Does non-transversal case affect?
I have to look it up. So you're absolutely right. There are the case by case by case by case. Are you blowing up, this and that? And well, so okay. So let me comment on
there is just the case what interest me. So, for example, the case when G-stable subvariety is tangent to G-fixed to fixed point locus.
So what actually happens is that the relations are completely determined by what happens on a surface. So if you want to understand the blow-up relations, it suffices to blow up an isolated fixed point on a surface. And you look at, there are like two eigenvalues, A1, A2, you blow up, you have an exceptional curve, and the only thing you need to do is to understand what happens to relations there. And then it turns out that all the blow-up relations reduce to this. A lot of complicated combinatorics, but actually that's the only case that you need to consider. An isolated fixed point on A2, or I don't know, on a surface with two eigenvalues, A1 and A2. And then what are the options? So, I mean, A1 and A2 could be in the same cyclic group and different groups. You know, the difference could be 0, could be not subgroup, this group, and so there are several options. So this is spelled out in great detail in the paper that's on my webpage, not on the archive yet, with Brendan Hassett and Andrew Kresch. There is like 2 pages where this case is studied in great detail, and indeed it implies everything else.
I see, and maybe this is one of the problems that you, as I understand, you don't have the theory for where the generic action of G is not free, yeah? So.
Sorry, generic action is not free. We didn't, no, we didn't write such a theory, but we have discussed it with Andrew. It's not that difficult to make that formalism, but we didn't think it's, I mean, it may be more relevant in the stack world than, you know, when you look at, yeah.
I see. Okay,
and so the point is, yeah, I understand where it's coming from. So let me expand on this. So initially, when we thought about specialization, we were thinking, oh, we could get this information from the strata. And of course, when you have a stratum, then you would have a situation where the group action specializes to something where, you know, you don't have, you're not generically free on the generic point.
Yeah, for example, your normalizer action, yes.
Exactly, but we are using not the stratum itself. The realization was that you have to use the total space of the normal bundle. And then the stabilizer, you see, on the total space of the normal bundle, if you had an action that was generically free, it will remain generically free. And so therefore, in our formalism, the specialization formalism that we used, we didn't need this, the study of non-generically free actions. But it did kind of occur in the thought process. And
it should be more complicated to choose the surface, yes,
yes,
for checking relations.
Yeah. But you don't need it. So because in applications, again, you look at the total space of the normal bundle.
Okay, thank you very much.
Mm-hmm.
Other questions? If not, let's thank Yuri, and so we'll proceed at 2 p.m. New York time. Thank you, Yuri, again.
Thank you.
Yeah, bye.
Bye.